Hey guys, boy Chill here. Welcome back to Hardware 3D. Today we're looking at something called PCF, percentage closer filtering, and another something called slope scale depth biasing. Just a bunch of words. And hopefully you'll know what they mean by the end of this video. Probably going to be longer than an average Hardware 3D video. Got a lot of stuff to cover. We're going to be dropping a lot of knowledge bombs down here that, you might not be able to find very easily on the internet and other tutorials. So stick around. Should be a good one. In the last video, we got our shadows working with all the stuff in our scene, and I drew your attention to our little problem here, which we gave a name. We called it Peter Panning. So let's talk about why our shadow is a little bit disconnected from our model here. All right, so we got a basic setup here. We got a light, we got a camera, we got a little bit of geometry here. We got a floor. Now, what do we expect for the shadows? Well, we would expect if we just draw a line from this light to the top of this geometry here, we would expect, okay, sure, this part of the floor here shouldn't be lit by the light, right? That makes sense. I hope I don't have to explain that. But in order to do those calculations, we've got to do a little bit of biasing, right? We have to, when we're calculating the depth of each position here, we're rendering from the camera. And for each one of these points that we sample and render, we are interpolating the depth with respect to the light here, right? So this would be for this point here, this is going to be the depth value with respect to the light. For this point here, draw a parallel line here because it's the depth in Y. This is going to be the depth with respect to the light. Okay? And what we're doing is we're bringing that just a little bit closer, right? Just a little bit closer so that the comparison works with the actual depth stored in the depth, what do you call it? The shadow buffer. Shadow map. That's what you call that thing. There we go. So what does that look like? Well, if we're moving all these points just a little bit closer, what we end up with, something like this. So the depth of this point has been moved a little bit closer to the light source, with respect to the Z-axis of the light viewing direction. We're just biasing that depth just a little bit. What ramification does this have? Well, obviously it's going to eliminate the self-shadowing problem that we have. We're not going to get shadow acne in this region. That's good. But let's just do some depth, some shadowing calculations here. So let's say, for this point here that the camera sees, what are we going to do? Well, we're going to calculate its depth relative to the light. So that is going to be, this length here. That's the depth relative to the light. Then we're going to bias that forward to this value. And then we're going to compare that to the depth recorded by the render from the point of view of the light. Well, what did the light see? For this point here, the light probably saw, this part of the geometry, the long, thin, whatever this thing is. So it saw this. It's going to record this depth. We're looking at this, but we biased it here. Oh my God. Now, according to our calculations, the thing we see is closer than the thing recorded in the camera's depth. And so this should be lit by our calculations. This stuff here is going to be lit. Only it obviously shouldn't be lit. It should be covered here. That's the problem with depth biasing. And what you get, the end result of that, you get this stuff is lit, obviously. This is lit, obviously. But also, a little bit here is lit as well. And then you get your shadows down here. So that's what causes the Peter Panning. And obviously, the less you bias, you make this bias smaller, the amount of Peter Panning will also become smaller. So with a small bias like this, you're only going to get a little bit of Peter Panning. And if you make it small enough, the Peter Panning will actually be hidden by the object itself, and so it's not really an issue. So long story short, in order to solve this problem here, we want to make our depth bias smaller forehead. And if we look at our Git history, that is the next thing. A very simple change. We're just going to change from 0.005 to 0.00005. We're going to make a much smaller depth biasing amount. And hopefully that is going to reduce our Peter panning. So here we are back in our scene with our shadow. And if we look at the footsies now, yeah, that looks a heck of a lot better. You might think to yourself, well, how can such a small change in Z, 0.005, move the shadow so much? And the answer to that, and it's actually ties in with a lot of problems that you're going to come in to with graphics, is because the depth value isn't our Z value, right? Depth, if we look at our rendering frustum here, very simple representation, the depth that is stored in the depth buffer isn't the Z with respect to the camera. It's the Z with respect to the camera, but it's basically like a reciprocal kind of deal, right? It's non-linear, non-linear functions, and they have some properties that we don't like. So, for example, and I'm just going to throw out some basic numbers. Let's say in our frustum here, this is 0 depth. This is 0.9. This is 0.99. This is, and then this is 1.0. You get the idea? So 90% of your precision is in this range here. And the last 10% is all in here. So this one gives you, about your remaining 10%. And then all of the minuscule rest of the precision is divided up into this whole big section up here. So what that means is, okay, you might be saying 0.005, that doesn't do shit. Sure. If you got a point here and you push it back by 0.005, it's going to be like, here. It's not even going to be here. So you can't even tell the difference. If you have a point here and you push it back by 0.005, maybe it's here. But if you have a point here and you add 0.005, you push that back now behind the end of the view frustum. So 0.005 means different things depending on where you start. That's the tricky part about non-linear things. They're kind of a pain in the butt. Kind of a big pain in the butt. And so what happens is that 0.005 can actually be a big deal for your depth biasing depending on where you are. So less depth biasing, obviously better, but as you might expect, there ain't no free lunch, and we're going to come back to that in just a little teensy bit. All right, let's switch gears a little bit. Let's look at a different issue that's going to tie all into our whole discussion of this video. So what I've done here is I've pulled the camera back a little bit. I've also made the light a little brighter. By the camera, I mean the light. I pulled it back away from the nanosuit. I made it a little brighter. So it's easier to see the difference between the shadow and the lit parts. And now we're going to go and look at this shadow on the wall up close. And what do you immediately notice? Yeah, it's blocky as shit. And this is another problem with shadow mapping that you're going to encounter. If you've played many games, it's not a particularly difficult thing to understand. When we render our depth values to the shadow map, it's got a fixed resolution, right? And then when we sample it, if we oversample it, it's the same idea as if you blow up a texture, make it really big, it's going to get all pixelated. And so we've got our shadow map, and it's basically, when we read from it, it's going to be all pixelated now. And I mean, there are things you could do. The most obvious thing that you could do to try to solve this would be, okay, when we render our shadow map, we're just going to render it at a much higher resolution. And yeah, that will make this problem better, but it's a brute force approach. It's going to make your engine run a lot slower, and it doesn't scale as well. Now, you might be wondering at this point, well, you mentioned textures, and when you magnify a texture, sure, it gets all pixelated, but we have bilinear filtering, right? So why isn't bilinear filtering working for our shadow map? We're sampling the shadow map with a sampler, and if you look at the shadow sampler that we have, let's see here. It's using the defaults, and that means that it should be using bilinear filtering. But obviously those shadows, they didn't look filtered at all. They were unfiltered as heck. Well, I mean, it just goes back, you gotta look at what we're doing in our shader. For our dynamic shadowing, we're not sampling the shadow map, the pixel values, and using that directly as a color. No, we're sampling it, then we're doing a comparison, a Boolean comparison, and returning true or false. Only two options, on or off. So obviously there's no way for that to be blended the way we're doing it right now. You're either going to have all shadow on or all shadow off. There's nothing in between. So you might be wondering then, well, then what is the bilinear filtering that we're doing on our shadow map? What is that actually accomplishing? And yeah, well, hold that thought. We'll come back to it. So the question now is, how can we improve the shadow pixelation situation there without having to increase the resolution of the shadow map? So look at this situation here. We're rendering shadow map from the point of view of the light. Got some objects here. When we render them to shadow map, you know, the circle is going to be closer. It's going to have a depth of 0.5, and the triangle, let's say the depth is 0.9. Doesn't really matter. All right. So the idea of filtering is a good one, but we've got to do it within the framework, within the concept of our shadow mapping algorithm, which is going to do a Boolean test, true or false. So what can we do? Well, right now, when we render from our camera's point of view, we see points in the scene, and we figure out what those points correspond to in the shadow map, and then we sample the shadow map at that point. What if, instead of just sampling a single point, let's say I'm trying to determine, you know, whether this thing is shadowed or not when I'm looking at it from the camera's point of view. What should I do? Well, I'm going to be looking up into my shadow map here. What if I also checked out the surrounding pixels? I can get an idea, basically, of whether I'm on the edge of a shadow boundary, and based on, you know, the percentage of these samples that pass or fail, I can adjust the amount of lighting that I actually allow through. So instead of just, our current system is just a if. If we are unoccluded, then do lighting calculations. Otherwise, do no lighting calculations. Specular and diffuse equal to 0. So what if instead of doing diffuse equal to 0, we can say, well, if half of them pass and half of them fail, do the lighting calculations and then scale it down by half. That's what percentage closer filtering means, PCF. So let's do another example. Let's say, you know, you're looking at this point here, this object here. Well, that's going to correspond to, let's say, this point here. And if you were to do the test, you would see, okay, this one is obviously behind this one based on our shadow map, so we will not light this one. But if you do PCF, you're going to sample all around, and you're going to see, okay, 3 of the samples are going to return that, yes, it's lit. And then 6 are going to return that it is unlit, it is occluded. So then we are going to apply 1/3 lighting power for lighting this pixel. And then what you're going to get is, instead of having a hard pixelated shadow, you're going to have a little bit of a smooth boy here. And that is going to reduce the pixelation. It is also going to give you an effect that we'll talk about in a second here. All right, let's take a look at the implementation of PCF in the pixel shader for the shadow. What we're going to do now is, instead of returning a bool, we're returning a float, right? Because we now have a range of shadowness. We're either going to be, if it's 0, that means that we're in full shadow. We don't want any lighting. If we're in 1, that means we're in full lighting. And if we're somewhere in between, then we want to modulate our lighting by multiplying it with the return value from our shadow function. So instead of naming the function now shadow unincluded, I just name it shadow. We have the shadow level. Again, if the Z position is greater than 1, meaning we're out of bounds, we're just going to return shadow level equal to 1.0. Full light if we are out of the range of our shadow map. Otherwise, we are going to do just a very basic, funky filter for the shadowing here. We're going to sample 4 pixels around the actual shadow map position. So we get the dimensions of the surface, and that will give us enough information to figure out how much we need to move in texel coordinates to get one left, one right, one up, one down. And we're actually going to do it 0.5, so we're only going to move, we're only going to sample 0.5. Just to show what that means, if normally we would sample here, we're now going to be sampling here, 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 here. We're going to be adding or subtracting, 0.5 of the distance of 1 pixel. So we pre-calculate here the biased Z. It's not really the Z, it's the depth, right? Depth biased is what I should have called it, I guess. Then, we sample all around the actual point. We compare with the Z biased. If it's greater, then we're going to return 0.25. Otherwise, we're going to return 0. And we add those all up together. So if they all pass, the result was going to be 1. If they all fail, the result is going to be 0. And if we are on the edge of a shadow, we're going to get some kind of value in between. So we got a range of 4 possible tones. Instead of just all shadow or all light, we now have a range of 4 tones in between shadow and light. So now, because our shadowing function doesn't return a Boolean, we have to change our if statement a little bit. I still want to be able to skip lighting calculation if we're in full shadow. So what I do is first I calculate our shadow level by calling our shadow function. Then I check if our shadow level is equal to 0. If it's not equal to 0, we do our lighting calculations as normal and we multiply by the shadow level. Otherwise, if it is equal to 0, we just set diffuse and specular to 0. We don't do any of those lighting calculations. This is probably an optimization, but you'd have to do benchmarking and real testing to make sure. Either way, it doesn't matter that much. So when we run it with this 4 sample kernel, we're going to take a look at the legs here, and it might seem a little smoother. It might be hard to tell. 4 samples isn't a lot, but if we look closer, we can see that indeed it is blurring the edges of these. We are getting, it's not just complete shadow and then hard into light. There are levels in between. And the more samples you take, the better that's going to look. But even with 4 samples here, we can already see, the blendingness, the blurriness is already starting to work its magic. And it actually looks better, obviously at a distance. Now, you guys want to see something real funky? Because doing this PCF stuff, it just opened a whole bag of worms, and we're going to take some time to cover that. Let's just see what happens when I move the light down towards the floor. Watch it go down. It's going down. Oh, and something's gone wrong. So here we're looking good, and booyah. Now, for some reason, the floor is completely shaded just by moving the light down a little bit. Obviously, that's not what you want. There's something going wrong here, ain't there? Now, the reason why we're getting this new self-shadowing that is somehow dependent on the height of our light with respect to the floor, this is really at the core of a lot of things that we have to do with shadow mapping. So, we need diagrams and we need them stacked because we got to learn this stuff. What we saw there with that self-shadowing, that's actually 2 problems stacking on top of each other. But those problems have a common source. They have something in common, so we got to learn about that source. So when we render a shadow map, we're rendering, to a fixed resolution surface. We're sampling the world at a certain sampling rate and recording that information. So if I'm rendering this geometry here, and we have a certain rate of sampling on our shadow map, we're going to sample pixels, here, here, and let's say here, right? This is our sample rate. So we're sampling the geometry at these points to generate pixels in our surface. There you go. There's your shadow map. More or less. Straight lines are hard. Just quit your complaining. Now, we're going to render the scene from the point of view of the camera, right? So let's say our camera is here. It's also rendering to a surface. It's going to render here, here. Now, first thing you're going to notice here is all the rendering here, we're sampling different points of the geometry, getting information about it, like its depth with respect to the camera, but we're comparing it with a single sample. This one here and this one here, they're going to be comparing to basically the same samples. So we do the shadow mapping, and we do the lookup back into this texture. This is what causes the highly pixelated nature, because we're taking many fine samples into a small region of the texture here. Now here's the problem. So our shadow mapping, what it does is it captures depth with respect to the light source. So here's our depth with respect to the light source here. It's this distance here. So for this sample, it's going to be the same. This sample covers a big range of the geometry. This one sample here. This sample here covers another big range of the geometry. Same story. Same story. And I think you can already see the problem, because the points, the finer points that we're sampling from the point of view of our camera, we sample this one, we get its depth relative to the light source. Then we compare it with the depth in the closest texel in the shadow map, which is this depth here. And so we've got a big error, because the closest sample that we can look up into was sampled at a different point on the geometry. Obviously, we can only sample at finite points. And the further away you are, your geometry is away from the point of rendering the shadow map, the less sampling frequency you're going to get per unit geometry length or whatever. So yeah, when you're sampling from the camera, if your point of sampling happens to land at the exact point that was sampled for shadow mapping, then you're going to get good data. But if your point of sampling lands here, you're going to get data that has a huge amount of error. This distance here is your error. So your maximum error is going to, occur at the boundaries between samples in your shadow map. And if you want to avoid getting self-shadowing for these errors, well, then you're going to have to add bias that's greater than this maximum error here. But of course, the more bias you add, the more you're going to get effects like Peter Panning. Now here's the rub. Here's the real problem. With PCF, when we're working with, let's say, this texel here, okay, sure, we're going to sample the closest depth, and let's say that's here. So we're going to get error of this for this sample, but we don't just sample the closest depth. We also sample the depths around that. So we're also going to sample this depth and this depth. And so we're also going to get a big error here and just an enormous error right here. So we're not just sampling the closest texel, we're also sampling the texels around that, and those depths are going to have enormous errors. So basically what this means is that if we want to use PCF, we want to sample around, we've got to build in extra tolerance. We got to build in shadow biasing that's, pretty big. And that's going to cause us problems with Peter Panning. So in this next commit here, you can see I've cranked up the Z bias, by a factor of 10 here to try to account for that PCF. And so you can see here with that, we're now able to have the light lower, and it's still not doing self-shadowing. But if I bring the light lower than that, eventually we still hit that self-shadowing. So it's not perfect. It's a lot better. We can get pretty low without hitting that self-shadowing, but it's still going to happen. And you can say, well, we'll just increase the bias even more. We'll make more bias. But the more you increase the bias, the more you get into stuff like Peter Panning. So it's kind of a nasty trade-off. Where's the tolerable middle ground? And that'll depend on, where can the light possibly be? Where is its range? What is the geometry like? And it's fiddly. It's not very cool. It's not the way we'd like to operate. Now, another thing you might be wondering about is, well, why is the height change the self-shadowing error? Why is it when I bring the light closer to the ground, then the self-shadowing, suddenly manifests? What's the difference? I mean, you would think, sure, it's the difference of the light to the object that you're sampling. More distance means a lower sampling rate per unit of distance in the object. And that's true, but that's not really the problem here. The problem is the amount of change in depth versus the amount of change in screen space, X or Y. So if we look at the scene right here, we've got this floor here. The part that we can see of the floor. There's the far reach and the near reach. So it's spanning some distance in depth. All right. And if we just think of it as an image, X and Y, here, as we move up in the Y, we're getting further and further away. This pixel here in depth is obviously much further away than this one here. If we move in the Z and the X, there is no change in Z for this current render. So we have a slope or a rate of change where we go further away as we increase Y for this floor. Now, so we have that's a slope. Like, we can calculate a rate of change. It's the amount of change in depth divided by the amount of change in Y. So for this distance of Y, let's say the depth change is 1. All right. Now, let's move our camera down. We're going to move closer to the floor. We're still going to be pointing towards the wall, but look at this now. It's a smaller change in Y, but the depth is still the same. So now the slope, the amount of depth that you get for every pixel you move up in Y, is increased. As you move closer to the floor, you're compressing this Y here, but the depth stays the same, and so the rate of change per pixel gets harsher. Each pixel covers a bigger depth change. And so now when you sample 1 pixel above, your depth error increases. So your error is really dependent on the slope of depth in screen space. So this is a very steep slope dependent on Y, but you also here have a slope that's dependent on X. If you move up in the Y, the depth doesn't really change, but if you move in the X, the depth is getting further away.